Welcome to those of you who are here. My name is Per Botner, and I'm going to talk about the open source scripting language Kawa, which is a project I've managed and been involved with for many years. Nope, wrong direction. So I'm an Oracle employee, but I want to make clear that this is not an Oracle project and is not sponsored or supported by Oracle. So this is my disclaimer. The takeaway, which we're supposed to put on the slide, is basically these points, and it's going to be a somewhat rambling talk. So if you have questions or things are unclear, feel free to interrupt. The things is Kawa is a mature, it's standard-based scripting language. Next, a very high-level non-pure functional language. That means it's a language where functions and expressions and pure values are easy and important, but it's not a pure language. There are side effects and assignments. And as far as I know, it's the fastest scripting language on the JVM, depending on how you define scripting language. And it provides a good balance between the static and dynamic properties of a program, which I'll talk a little bit about more. And so first, okay, we know scripting languages have a lot of buzz the last few years, very visible and popular, but what is a scripting language? Contrasted to a programming language. And there isn't really a difference. It's a matter of degree. But common properties of what we think of might be a scripting language is that it has immediate evaluation. You don't have to have a separate compilation step. If there's a compiler, it's automatic. It runs when needed. There's typically, you can evaluate expressions immediately. There's an eval function, and there's maybe a read eval print loop that is, a command shell. It has less boilerplate. You don't have to say, class something, function main, and all of that stuff that you have to with Java. There's usually less syntactic verbosity. And programs tend to be, on the whole, more dynamic, less sort of fixed when you write a program, and more things on the fly. So one issue with scripting languages is they tend to be very slow, relatively speaking, which may or may not matter depending on your application. Here's some benchmark numbers. These are the so-called shootout benchmarks. And with all these numbers are relative to the Java runtime. So higher numbers are slower. And Scala is usually considered not a scripting language. It's sort of heavy duty, it's a little hard to learn, and it's not as agile as other languages. Clojure and JRuby and Kawa are perhaps more scripting language side. You'll notice Clojure and JRuby are significantly slower than Java or Scala, and significantly slower than Kawa, which is the language we're going to be talking about. Now, there's a little bit of cheating because Kawa has optional type declarations and a smart compiler, but of course, those are things that are very useful if you care about performance. And cut down on the arms. It's not just speed that's important when you're comparing programs and programming languages. You also care about how productive it makes you. And being too dynamic makes it hard for your compiler and IDE to detect errors at compile time. And we all know the earlier you can detect errors, the faster, the cheaper it is to fix them. And your typical scripting language just has runtime type checking, which means the way you detect an error is you get an abort runtime error, and then you have to figure out what caused the runtime error. And so if you have, for example, static types aren't just, they let you annotate your program with things that let the compiler catch errors. Since we all programming in Java as well as other things, so you know that that's good. And also not just catching errors, but also analyzing the program. You want to find, given an identifier in a program, where is the declaration, the definition of the identifier. And if your language is very dynamic, it depends on what the execution path is, what gets loaded what, in which order, and you can't really judge where the definition of the variable is. So there's the trade-off here, and that's a big trade-off in programming language design. What aspects of a program are static and what are dynamic? And static aspects, the things that are fixed in the program, fixed at compile time, are things that make it easier for the compiler, the type checker, the ID, and the human to figure out what's going on and analyze the program, understand it. On the other hand, whatever is dynamic, the things that change at runtime, they make the program more flexible, more agile. You can do things on the fly. So as I said, the key issue is what is the right balance, and I think Kawa has a fairly good balance there. It lets you get good performance, it lets you get good error checking, but it lets you do all the dynamic things that are most useful, in my opinion. Okay, try that button didn't work. Try it there. I think I went too far there. There's a slide missing, I think. Yeah, there's a slide missing. Oops, what happened? What happens if I just use this? Okay. There was supposed to be a slide about dynamic versus lexical scoping of local variables, so I guess I'll have to wing that. Somehow it disappeared. The classic rookie mistake of people designing their own programming language is you make dynamic scoping of local variables. And a similar related mistake is, the variable appears automatically if you assign to it. And this seems appealing to people who don't have a lot of experience with programming languages. It's simple, it's easy, it's convenient, but once you get more experience, it causes all kinds of problems. And experience teaches us that lexical scoping, closures, Lambda expressions are much more useful in general. And so that's where, Kawa, which is a dialect of scheme, was perhaps the first important language which actually had lexical scoping in terms of what we now may think of as a scripting language or a very dynamic language. Okay, so now let's see if the slide that was following the slide that I just improvised. As an aside, dynamic scoping does have its uses. It's not a completely useless feature. For example, for context parameters like the current open file or the current paint or state of your program, it is sometimes convenient to basically have that be inherited dynamically in the state. But it shouldn't be the default for your local variables. And Kawa has functionality for dynamic bindings. It has a fluid let. The dynamic bindings are also called fluid bindings. And so it has that functionality, but the default is lexical scoping, which is the right thing. And a slightly harder to read slide. Another example where the trade-off between static versus dynamic comes into effect in programming language design is how are classes defined. And in the classical, semi-intended, is that classes, you write them in the program, they have a name, they're fixed. You can tell what the name, from a name of a class, you can tell the definition of the class. It's right there. But some languages instead have prototypes. Basically, any object can be sort of act as a class for any other object by providing the defaults for it. The most common, best known example is JavaScript. Some languages for example, some languages, for example, Ruby, allow you to add methods to a class dynamically. Basically, that's how classes are created, by adding methods to them. And these properties, first, they make implementation a lot more difficult, needlessly more difficult, especially on the JVM. But even if you have a custom VM, it's difficult. But more importantly, it breaks modularity. It pollutes the global namespace with things that changed in weird ways. Given a class name, if your class can change underneath you, you don't know what it is, what it can do. It makes it really hard to keep track of, understand what's going on. And it's also, again, right now, we all know parallel programming is the big challenge. And part of the solution appears to be immutable state. And if you have mutable classes, then immutable state becomes so much more difficult. So the conclusion is, keep your classes static. You can always create classes on the fly, if you have a val or something like that, but your basic define a class mechanism needs to be static, or should be. Last slide on classes, an aside on multiple inheritance. Yeah, Kawa has conventional classes defined in the program text with all of the fields and methods in the same place. But it does have full multiple inheritance. That is, a class can extend multiple classes. And Java 8 is finally getting multiple inheritance for interfaces, in that you can, with default bindings. Kawa also has multiple inheritance of fields and state, which isn't as useful, but it's occasionally useful. And it just makes things simpler and more consistent. And Kawa also has properties in the sense that the compiler kind of hides the difference between fields and methods, or getter-setter pairs. So if you can use something that looks like a field reference, and if there isn't a field, but there's a getter-setter pair, it'll use that, and vice versa. So let's try the next one. Okay, now back up a few hundred feet. So the Kawa language, which I've basically written since 1995, is a language in the Lisp scheme family of languages. And scheme goes back to 1975, and was the research of Guy Steele, who is also well known for the Java language specification. Its scheme has been standardized a number of times. Informal standards. There's a new standard. The seventh revision, R7RS, is expected later this year, or maybe early next year. And because of this, or related to this, there's an active community of many implementations, and a number of them is still active. There's also a number of historical implementations. It's been used a lot in academia for programming language research and teaching. It's basically the prime language for experimenting with dynamic languages, scripting languages. And Kawa is more or less compatible with the scheme specifications. It implements basically all of the current specification, which we could argue whether that's R5 or R6, and that's a contentious issue, with lots of popular extensions. The main thing missing before people ask is that it does not support full continuations at this point. And implementing those is possible, but it's difficult, and it's not clear. It's never been important enough to come to the top of the priority queue. So the thing that is most obviously noticeable about the families in the Lisp scheme family, languages in that family, is the way function calls look. The lots of Lisp is said to stand for lots of irritating silly parentheses. So the function call notation is, how does this thing work? No? What do I, oops, nope. And, okay, so sorry about that. Okay, let's just easily go through here. What was it? Yes. Okay, so we will point by hand. So this is your prototypical function call expression. It's basically, these are all expressions that get evaluated. And then the first sub-expression has to evaluate to a function object. And then the others become the operands or arguments to that function which then gets called. So here's an example. If str is bound to a string, this gets the substring from I to j of that string. And so substring here is sort of a variable, but it's a constant. It's a variable that's bound to a function. So in general, this could be an expression, but usually it's just a variable name. And for consistency, this notation is also used for arithmetic. So this adds these three numbers to get 6. Now, we use the same prefix syntax for control structures. For example, this conditional here, it's this sort of if expression. If this is the condition, if I is less than 0, notice the less than is also in prefix position, then negate I, again, in prefix, otherwise return I. So it's basically an absolute function, yes?
I don't know, speaking of Kawa or scheme?
And right now I'm speaking of scheme in general. Yeah. This slide and the previous slide is scheme in general. And similarly, assignment has this built-in operator, which looks like a function, but it's a special built-in operator, which assigns the value of this expression to the variable named abs I. And this is not a subtraction; it's a hyphens can be in variable names. In general, these are all identifiers. This is an identifier. The less than sign, the minus sign is an identifier. There's a fairly rich syntax for names in the scheme Lisp family, which means you have to put spaces, which is what you want for readability anyway, and you don't have to have commas. So there's pluses and minuses of this syntax. And finally, variable definition defines this variable to have that value. Still general scheme rather than Kawa, except for this sentence. So as I said, scheme is a functional language. It's always had anonymous Lambda expressions or Lambda functions, which is a little like Java 8 if you're familiar with that. And this is a keyword. It's it's predefined Lambda, a parameter list, and then an expression. So this creates a function value, which with these parameters, and then when the function value gets called, this expression is evaluated in the context with the parameters bound to the actual arguments. And then this can be assigned and passed around. This is a general thing that it's an object, but it's an immutable object. Though it may depend on the lexical state, because that's what lexical scoping means. So there's an example here. This is the same absolute value expression now as a function with the parameter I. Return the absolute value of I. As a Kawa extension, if you use a Lambda expression in a context that requires a special class, an interface that has a single abstract method, then the Lambda expression gets turned into a method of an anonymous class. Very similar to Java 8. But the difference from Java 8 is that you can use these Lambda expressions even in an untyped context. You can sort of, if you have the equivalent of object X equals Lambda expression is meaningful, but it's not meaningful in Java 8. Because Lambda expressions in Java 8 are only meaningful in a context with a target type. In Kawa, if there is a target type, it will do this automatic conversion. But if it isn't, it'll be a generic function value. And of course, you can name functions. This special syntax here defines apps as a function with the parameter I and the body here. And this is basically just syntactic sugar for defining apps as a variable that you initialize to this Lambda expression. So yes, this syntax is a little weird, maybe. It's consistent and it's simple. It's not what we're used to, but it has some advantages. The main one is that given that the core syntax of these prefix expressions, prefix forms, is very simple and general, it makes it easy to extend the language and define your own forms. Basically, a macro is fairly easy to write. People do it all the time. You don't have to be an expert to do it. And it's basically mapping from a source expression, a form that's in the source program that the programmer writes, and then it maps that into something implemented in terms of primitives or other kind of macros. So it's a rewriting to a simpler expression, and then so you can basically define domain-specific languages or whatever kind of syntaxes you like. And the key thing. So in the macro call or a macro invocation, you call it the same way. You have a macro name and arguments, and then these get passed to the macro transformer, and then get compiled, evaluated just like it was a built-in. And so having this this prefix syntax consistent makes this a little easier. And you can define macro systems, extensible syntax in other languages, but they tend to become, they haven't been very successful. It's difficult to do. But it's mainstream in the Lisp scheme family. And the if and define forms in Kawa are actually implemented as macros in terms of lower level primitives. Just move on a little bit. This is now not scheme general, though there are other scheme implementations that support the same syntax. This comes from a language called DSL, this actual syntax. DSL, DSSSL it was a precursor to XSLT, which was basically a scheme dialect. So this defines a function, Z, which takes, this is a magic little word, which means that the following parameters are keyword parameters. So there's re and im are the names of the parameters, and they have default value 0. And the function calls make rectangular, which creates a complex number with those values. And so here we define the imaginary constant as Z with im set, the im parameter set to -1, and the real parameter defaulting to 0. So I think time for a little water. So an example where keywords and keyword parameters are useful is, for example, if you want to deal with XML, HTML type nodes, where the convention that this function make element creates a node, a element node, and the convention is that keyword parameters become attributes. So this has a evaluates node whose element node whose tag is p with an ID attribute valued p0, and the body as the concatenation of the string sum colon and whatever the value of the variable sum is. Which, you know, is a little clumsy. So Kawa actually has XML literal syntax, which looks like this, which is basically regular XML syntax, but prefix, this hash sign is a sort of a standard syntax extension. It's used for a number of little things to indicate, well, depending on what the character is after the hash sign, it can mean all kinds of different things. So this is the Kawa extension that hash less than is an XML literal. And here it's sort of, okay, evaluate this expression and substitute it. And you can have sort of evaluate, the tag name could also be an expression that gets evaluated, in which case you can leave out the final tag. So again, a more important, or this is perhaps a variation of general object construction using name parameters. Keyword parameters are useful for basically object builders, which I'm going to talk for a few slides here. Start out with the case where you have a type name, usually a class name, but it can be something else. Basically a class name, a keyword, a value expression, keyword, value expression. So basically this evaluates the value expressions and then sets the name properties. So these keywords are assumed to be property names. And this is general. It doesn't need any special magic. It doesn't need any special builder property or anything. This just works with the built-in stuff. So for example, it assumes it works as long as the class has a default constructor, and then for each keyword there is either a set method or an add method that matches. So here, for example, you have create a swing J button with, and then it calls set text using this parameter and set tooltip text using this parameter. Scheme and Lisp traditionally use, instead of camel case, they use hyphens. So Kawa magically translates back and forth between camel case and the hyphen thing. But you can use whichever you prefer. Another variation of object construction is sequences, lists, arrays, things that have children, which includes XML elements have children. So in this case, you have the type name followed by the list of children. And this is actually conventional, this is standard scheme. This particular form, vector, is a built-in function in scheme. It creates a new vector, which is basically the same as sort of like array list with these parameters. So Kawa kind of changes the meaning of this a little bit. In scheme, vector is a predefined function. In Kawa, vector is a type name, which means you can also use it as a type specifier in declarations, but you can also use it as a constructor function. Basically, if you have a type name, types are, a little aside here, type names can be evaluated at runtime. They're basically an expression that returns either a class or something else, but basically let's just call it a class. So in this case, this is an expression that evaluates to javautil.arraylist.class. And then if you call a class, there's a magic in Kawa that says, oh, well, you can't call a class, but let's call the constructor instead. Or in this case, but there's also a little extra magic. If it's a list or sequence or an array, construct the sequence. And so here we create an array list and add the elements. It assumes there is a default constructor and an add method, and then it just works. Doesn't need any special magic. This also works magically. It also works for native Java arrays. So here's a Java lang integer array with 3 elements. And this is a little more magic. Here's a array of ints. So here's a little context-dependent type. This is a special Kawa extension syntax. It's sort of like the vector constructor for 5. It creates an immutable vector, but it's context-dependent. So if the compiler, I need an int array here. So instead of creating a vector or an array list or whatever else, it creates an int array. And so this becomes an int array, this becomes an int array, and then the two together becomes a double nested array.
So from where does it know that my type name is a container?
Sorry, when does it, how does it know that the type name is a container? I have to look back at the code. I think it is basically, there's this complicated code there, but partly it is, if it has a default method and an add method, that's all it needs.
So it also works for custom types at the right of the
Yes, as long as you have an add method. It works for, I'll show you an example later where you have things like JavaFX scenes where you have nested sub-elements. There's a little bit of custom magic there, but basically the general thing, as long as you have an add method, it will say, oh, okay, if there's an add method, it knows these are children. And so it just add them to the constructor thing. Now, there's a special, obviously arrays don't have add methods, but it sort of special cases those. And the final part of the constructor syntax is a regular constructor. So if you have a type name, these are treated as constructor arguments. So there's a little bit of ad hocery. It has to say, are these constructor arguments, or are these children that get added after things get constructed? Usually there's no ambiguity. But there's also a special case. If there's no constructor, then the compiler or the runtime will look for a value of method, which allows you to basically use the same syntax for factory methods. And I think it's actually kind of a good principle of language design to try to hide the difference between factory methods and constructors, because they may change depending on your needs. Sometimes you may want to cache something and reuse a previously constructed object, and if you have to have a different syntax for new t rather than t of using a factory method, I think that makes your program less flexible, your language less flexible. So Kawa tries to make that more automatic.
And if there are ambiguities, can I force it to treat the arguments?
Yes, let's get to the next slide. If there are ambiguities, how do we deal with it? Well, first look at here's the general case. The general case is you have a class or type name, you have constructor arguments, you have keyword arguments, and then you have child arguments. So the constructor arguments are passed to a constructor function. The keyword arguments are used for setters or add methods with named add methods. And the child arguments are used for children, and so there needs to be an anonymous add method. Now, what happens if there are no keyword arguments? How can you tell whether they're constructor arguments or child arguments? In general, it's context dependent. There is a hack you can put in. You can use a null keyword, which is documented in the Kawa manual if you need to actually disambiguate it. But it's pretty rare that that's needed. Water break. So this is like object builders in Groovy and other languages. But the key thing is it's fairly general. There's no special builder class needed in most cases. The compiler figures out by heuristics and method names and says, okay, this works. And most of the time, it can do it at compile time. It doesn't, so it generates basically the same code as if you programmed it by hand in Java. It generates very efficient bytecode. Now there are cases where this general heuristics aren't really what you want. They don't find the right methods, the right properties. So there is a hook for overriding it. And here's an example where this hook is used. I haven't talked, how to write the hook is a little black art, but it's relatively simple code. It's just not documented. So here's how for JavaFX has these properties that various nodes have that you can modify. You can set the properties and add things, but you have to go through an extra indirection, and there's extra builders and stuff like that. and which means this kind of code isn't going to work out of the box. Kawa won't be able to find the right methods and figure out that these are property names. So there's a little helper class you have to include a macro, which is pre-written. You know, the Kawa library has a special module. If you include that module, it enables this stuff to work. And that adds some extra special compilation rules to say, oh, if I'm trying to compile a JavaFX button or whatever, then I need to go through this extra step to get this to work. And in addition to the object construction here, there's a few other interesting things here. First, JavaFX scene is a macro that's rewritten in that library module I mentioned, which creates a scene and a stage and puts them all there. So basically, this is a complete program. You put this in a file, you load it, and a scene with a button and you can set the title of the window. So it comes up with a window, and you can set these properties, and you don't need to do anything more. You can also set you can also set event handlers by using Lambda methods, and this uses the SAM conversion that I mentioned earlier, i.e. there's an anonymous function, but this context requires an event handler. So we'll treat it as an event handler, and it'll compile to an event handler rather than to a function. And a lot of these things, a lot of these constructed things will work whether in interpreted or compiled text, but there are some subtle differences because, unfortunately, the Java type system, method overloading and stuff like that is a little bit magic. It doesn't work quite the same if you don't have the static types, and so that's an aside, which I think is kind of. But if curious, I'll go into it. Switch to a slightly different topic. One of the key things about Kawa, modularity-wise, is it's very simple, and that a source file is a module. The unit of privacy. Private versus public is a source file. And that's very simple. And a module, what's a module? It's a collection of top-level definitions, variables, functions, classes, macros. Can also be top-level actions which are executed when the module is loaded. Some subset of the module top-level definitions may be exported, others are private. And you can import another module, which basically means the module gets loaded, and the exported names from that module get then imported into the namespace of the current module, but not automatically re-exported. But you can re-export if you explicitly re-export. Yes, okay, so the other thing is such a module basically compiles into a module class. So this is obviously simplified, but basically you have an optional module name declaration. If you don't specify it, it's inferred from the name of the source file, which then generates a similarly named class file, or class, you can specify which top-level definitions are exported. In this case, only G is exported. So you have a function f and a function g, and a variable val2, which is not exported. And these compile into methods and variables, and there's a little bit of magic and stuff like that, but that's the sort of very high level what goes on. So by default, such a module gets compiled into a static module. That is, everything is static. But you can have non-static modules where things are instant modules, instant variables. And that can be useful if you have like per constant properties, where modules can be, depending on your context, depending on your HTTP session or whatever, things like that. But basically, they turn into statics is the normal case. Of course, yes. Of course. Huh? Yeah, this is a simplified equivalent Java of the generated bytecode. but yes. One key property of the module system, which it sort of inherits from R6 scheme, is that all of the exported variables and definitions are read-only. You can't export a variable and then assign to it from some other module. I mean, read-only, they're exported read-only. They can only be assigned to within the module. This key property, so to speak, enables, is very helpful for the compiler and error checking, and in general, because and modularity, safety. It seems a very good idea, which I got from R6 scheme. It improves the data flow analysis, data, type inference, error checking, just having that. So of course you can call a function which changes a variable, but you can't change it directly. A few more words. We're getting close to the end here. But this gets into some more heavy-duty stuff. Unfortunately, I didn't really write any good examples here. Variables in Kawa scheme, and this is an extension. Standard scheme is completely dynamically typed. There are no type specifiers. Kawa has type specifiers. You can sort of you can say, define x : integer whatever, and that says that x has to be an integer. And do that for parameters and local variables. But key things that those are optional. You don't have to specify the type specifiers. If you do, it will allow the compiler to generate better code. It'll allow the compiler to catch errors at compile time, or earlier at runtime. It's also if you have a type specifier, it gets enforced at runtime with some kind of cast. So if you even if the error is caught at runtime, it gets caught earlier, which means it's easier to debug. So the optional type specifiers combined with data flow analysis allows the compiler to generate pretty efficient code, as I showed in the earlier slide. And as I said, they also allow the compiler to catch a lot of errors early, which improves your productivity. And Kawa has a lot of warnings that you can switch on and off, and you can switch them on and off locally. You can bracket an expression where it says, turn off this warning and this sub-expression or in this file. So you can then enforce, and there's also a switch to say, make all warnings be errors. So if you can combine those two, you can sort of have your compiler catch a lot of errors early. I think it's always a good mode to compile with warnings be forced as errors, but not everybody wants to do that. Back to your question about what happens, a little bit, a very quick summary of the logic of the compiler. The first step is the text of the program is read into what are called the S expression, a list representation of the parentheses notation, basically. So everything in the parentheses becomes a list, and then it gets into this tree format, which is the traditional way scheme and Lisp languages do. And then the next step, which and that happens for that means that's part of the data. Did I have a slide for that that also got missing? And to step back, there's the duality between yes, I did have a data file slide for that at some point. I don't know where that ended up. These parentheses expressions, they can also be data, and you can quote an expression, and then it becomes just a list, or you can evaluate a list, and it becomes an expression which then gets evaluated. So this duality between code and data is a signature property of Lisp family languages, which means basically a program is sort of an interchange format. So yeah, you get this. So the first step is you read the program as data, and you get basically a data representation of it. And that's raw. Then you need to actually start analyzing it. And the first step is you do the lexical name resolution, you do the macro expansion, and a few things like that, and you get then an internal Kawa format, which is an expression tree, which is your classical, abstract class expression and sub-expressions for if expressions and lambda expressions and stuff like that. Then there's a little preliminary analysis, which I won't go into. Then the big phase is the data flow analysis, which also does a fair bit of rewriting. So it'll do constant folding, it'll do simplification, it'll keep track of, I'll say a little more about on the next slide about that. But that's the big heavy one. Then we do get into the low-level stuff. We've analyzed the program. Now we need to say, okay, we have these anonymous functions, these lambda expressions, and they may refer to variables that come from elsewhere. How are we going to translate that into objects and classes and methods? So we do some analysis figuring out what local variables have to be allocated in an object of a field in the class, similar to the way anonymous classes in Java had the same issue. How do we do that? Then finally we generate bytecode. And then the bytecode either is written out to a file for future use into a class file, or we just immediately evaluate it. If you have a read eval print loop, it just gets compiled to an array, a byte array, and then the class gets class loaded defined class, and then you you call it an appropriate method and evaluate it. As mentioned, the most important and most complicated pass in the compiler is the data flow analysis pass. And it was complicated because there are all these dependencies. Everything depends on everything else. It also has to be done at the same time. And you get an approximation. You can't, because if this is a constant, that influences something else. If this function calls that function, it'll. So it's. But it's basically it's a tree walker. It visits the expression and calculates properties. The types of the expression. It also keeps track at every point as it's visiting the tree what, for each local variable, what assignments or initializations may have set that variable. So so it knows that, okay, so you can do like constant folding, for example. You can also say, okay, I know the type of that because it was set in this assignment. And you can check for uninitialized variables in a smarter way than Java does. There's also some special hooks for certain known functions like arithmetic. The map function, which does sort of a maps over a lambda expression, sort of kind of like a funny kind of a loop. That actually gets translated into a loop. And so there can be hooks to special functions which then rewrite the tree into a different format or simplify it in various ways, including constant folding. This should have been basically some of this data flow analysis is similar to the classic single static analysis, single static assignment SSA analysis, which is traditional, has become traditional in compilers for languages like C, C++. It gets a little harder when you have functions, first class functions, where expressions can evaluate to functions, and it gets even worse in Scheme because basically there's no such thing as a loop per se. Basically, all loops are defined as tail calls or tail recursion. And there's also a fair bit of analysis for figuring out when tail calls can be implemented as loops and when functions can inline. If you have mutually recursive functions that call each other with tail calls, the stack's going to explode unless you have tail call elimination. And so Kawa does this analysis to say, oh, these can all be compiled into a single method, and all of the tail calls get compiled into go-to statements, basically. And the bytecode has go-tos, the Java language does not. So the analysis is going to be approximate because I try to do things linear time. I only try to analyze each piece of code once, and so you're not going to get perfect results, but it does pretty good.
Is it written in Kawa itself?
Most of it is actually written in Java. The libraries and built-in functions are written in Kawa. Kawa is actually, I haven't really gone into it, but it's actually kind of a framework. There's actually multiple languages that it supports. There is an xquery implementation. Xquery is this language that the W3C did to process XML, basically to search and analyze and query XML. And it's a very different style of language. And there's also, and it uses the same engine, the same compiler. It parses it, builds the same expression trees, generates bytecode. So for that reason, plus that it simplifies bootstrapping, most of the compiler is written in Java. But as I said, I'm sort of gradually moving, at least built-in functions. I'm trying to do as much of the built-in functions as in Kawa. But the core language, the compiler itself is pure Java. Yes.
One more question.
Uh-huh.
Do you cope with the problem that Java doesn't have pair recursion by eliminating it at this level already? So
Yes, but you can't do it in every case. There's a non-trivial analysis. The simple case, the common case, when you have, a function calls itself in a tail call, it's easy to just, okay, I'm just going to implement that as a loop. But it might tail call some other function that it doesn't know. People comment, if you have like delegation, and this is why some people say, tail call elimination is necessary for object-oriented programming. If you're going to say, I have this method in an object, and I want to delegate it to some other object, which may delegate it to some other object, which, etc. That's going to potentially blow up your stack, or at least unless these delegations can be implemented as tail calls. But you can't really do that if you don't know what you're delegating to. So what Kawa does a good job of tail call elimination to functions that call themselves in a sort of group all in the same module. Says, okay, function F calls function G, which calls F and H, and they're all kind of have these properties, so I can all compile them into one method and do gotos. But if you don't know what function you're tail calling, you can't do that. Other one is Kawa has an option. There's something called a trampoline where it has a compiler switch which says, support full tail call elimination. And there's a trick where instead of, if F calls G in a tail call position, instead of calling G directly, what it does, it remembers G in a special context variable and then returns immediately. And then there's what's called a trampoline. There's a sort of an outer loop that says, okay, I'm not done. Somebody asked me to call G after I called F, so I'm going to call G next. And so you can get the tail calls executed without expanding your stack. The problem is it adds overhead, and it's not really compatible with the Java stack, so your IDE and your debugger doesn't understand what's going on. So it would be really nice if this was sort of built into the JVM, but it has to be kind of built into the JVM, and it has to be built in. It's not an optimization. It's something that's part of the semantics if it's going to be supported.
But also by eliminating it all in one function, we have the problem that we can debug meaningful things. And you don't know the stack that you have.
Right. Well, as I said, that's part of it. It's part of the semantics. The tail call elimination isn't an optimization. If you think of it as an optimization, it's going to change the properties of the program because your stack is going to be different, which is going to change debugging, it's going to change the security model and stuff like that. If you say the tail call is defined as a tail call to sort of get rid of the stack, then it's part of the semantics, and it's basically a loop, and it's what it is. I think I have one or two more slides, so let me finish that. I mentioned that part of the way Kawa generates good code is that various predefined functions, they have various custom hooks to optimize them. For example, addition. And there's two hooks. One, there's a hook that's called at the data flow rewrite time, which is used partly to simplify and partly to infer type. So you say, okay, if I plus j, and I know that I and j are integers, then the result is an integer. There's also a possible set of hooks for bytecode generation time. If say, okay, I'm generating bytecode for I plus j, or plus ij in scheme syntax, then if I know these are integers, and specifically if I know if these are 32-bit integers, then I can just generate the JVM IAD instruction instead of making a method call and object allocation, et cetera, et cetera. So a lot of these built-in functions have custom hooks to generate custom bytecode and do custom type inference, and that's partly why I can generate good code. And that's the info slide. So any more questions? And I think, yeah, we're pretty good time-wise. Yeah.
For the XML literals, given that syntax, how do you then print out unreadable objects? Because usually at the...
How do I print out what objects?
Unreadable objects.
Well, these are, question was, XML literals, if you print them out, how do they get read back in again? Or
For objects that are usually unreadable, in other words, you have syntax which would look like the XML literals there. So in that case, what do you do for unreadable objects?
Well, they will print out using the same syntax, so they are going to be readable. But it's a little bit of a issue there in that what is the difference between the literals that are literal at read time, as in read in by the low-level scanner, as opposed to things that evaluate to whatever they evaluate to at evaluation time. So yes, not everything will be readable in the same sense as, but XML literals should generally work. They will print out as using the XML literal format, and so they can be read back in again.
I'm asking for objects that don't have a specific readable representation. How do you represent those?
That's a general problem with you can't. You may just call a toString method if it has one, or there's a special interface it may call. Sometimes you will get objects. If it's a random Java object, if you print out a JavaFX swing J button, well, it's going to just call the toString method of the J button. You can't read it back in again. In general, it's not going to be a perfect serialization format. Behind you?
It's very interesting that it supports multiple inheritance.
Mm-hmm.
How did you deal with that? Because most of the languages. Kawa has actually two methods, two forms. There's defined simple class, which generates a single class. There's also defined class, which supports multiple inheritance, and that it works by basically compiling a Kawa class into both an interface and a class. And so the class contains each of the methods that are non-abstract get compiled into a static method in the class, and then subclasses will have to sort of generate stub functions that then call these static methods as necessary. Same with the fields and properties. They are basically compiled in the interface gets getter and setter methods, and then a class has each subclass has to sort of automatically generate the setter and getter methods to set the properties. Too confusing? Yeah.
Yeah.
Thanks.
In the back?
There's a whole bunch of new proposals for extensions to the Java virtual machine, particularly this dimension machine, which supposedly can do continuations. So where are you with it?
Okay. There's a bunch of research projects
that people have done to implement continuations, to implement full tail calls. Another interesting one is structures or tuples. None of these are in any imminent danger of being shipped or being integrated in anything. There is no whatever continuation support there is in the Da Vinci machine or whatever, or the kitchen sink language as some people call it, are highly experimental, and there are no plans to turn them into a standard part of JDK, unfortunately. And that's because of, and some of these things are clearly, everybody agrees that, John Rose, everybody agrees, it'd be really nice if we had proper tail call support. It'd be nice if we had really support for efficient tuples or structures. And so somebody makes a prototype implementation, but that's only a small fraction of the work needed to actually get it shipped, because you have to standardize it. There's all the politics, there's the specification, the test cases, the TCK. A couple of years ago we got Invoke Dynamic, and they're working on improving that, and maybe in a couple of years we'll get tail calls. But don't hold your breath, because the people who can do the work, in terms of actually, employees who can actually, make it more than just a master's. A master's research project is one thing, but something that can be part of a specified product is a lot harder. Yeah. Yes.
How can you run this in shebang style scripts?
Yes. 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 There's something in the manual about how to do that. There's a couple of different ways of doing it. There's the usual problem with but yes, you have to specify the interpreter explicitly, or you have to do some other magic. But basically the Kawa command line. You say Kawa, and by default it comes up with the read eval print loop. But you can also say Kawa foo.scheme, and it'll load it, or so it. No, it's part-time. I'm trying to cut down and so it sort of, depending on what my day job is, depending on whether I've taken, there was a few years where I was working as a contractor working on Kawa, and I actually did manage to get enough money to support myself. Right now it's been difficult. So for that and other personal reasons, I'm trying to cut down to maybe working half-time at Oracle. Hopefully then I'll have more time on Kawa. Because I have this queue of things I want to finish, or features that I want to add, and documentation I want to improve. The website is not sexy, for example. It's trying to get people to use it. Leads more PR, which I don't have time for.
Sorry, I missed the first part of your presentation. Your presentation said high performance scripting. So where does the high performance come from?
Oh, that's the whole talk, unfortunately. But I can show you this is the numbers. Unfortunately, I didn't. These are I prepared these numbers for Java 1 2 years ago. So they may be a little bit of a lie. I tried to update them, but I kind of got overwhelmed with personal things. But basically, these times are relative to Java runtime, and you notice Kawa is a lot faster than JRuby or Clojure. It's comparable to Scala, basically. And the talk is partly explain how and why.
Can you actually expose local friends?
Can I what? Sorry.
Can you actually expose the threading model of Java?
Well, I've done a little bit of work there. I have lazy evaluation in futures and promises, and something I want to work more on. But it doesn't hinder the threading model, but it doesn't have a lot built in, except for it does have some syntax for futures and promises, which give you sort of automatic synchronization. So there's a little bit there, but not as much as I'd like.
if there are any more questions, just talk to me personally. I think we're kind of over our time technically, so or talk to me while I unpack. Thank you very much.